Alright, in this video we're going to be looking at how to solve application kind of problems. So application problems usually involve some type of real world scenario, and we look at how to use math to answer that question. Now in this example we're going to look at this scenario where we want to set up a dog fence using a side of the house as one side of the fence. And we currently have 100 feet of fence. So you can see we have an illustration here showing this happening. Anytime you're solving application problems or just solving math in general, it's always a good idea to have some type of visual representation because it helps our brains understand what we're looking at or what we're trying to solve when we can see it. We just seem to process that a little bit better. So you can see we have our house set up and we're going to have the fence on one side of our house. Now the question that we're trying to solve here is, how can we design the dimensions of the fence to have the greatest area possible? So we're looking at what we want to know is what are the dimensions of the fence that will create the greatest area. Now at first glance or at first thought, it may seem that the area would be the same regardless of what size fence we have, of what our dimensions would be. So let's talk about the area here of our fence and look at some examples. Sometimes when you're trying to solve an application problem, it's helpful just to try some scenarios instead of trying to get too deep into the math. And then once you understand the scenarios, you can move over to trying to develop the math that will model this problem. So I'm just going to refer, when we're talking about rectangles, a lot of times we're talking about length and width. So let's call this side L, and then we'll call this side W. Well, if that's the case, I could then create a table just to look at some scenarios. So I could say, well, maybe let's look at what happens if the length is a certain measurement compared to the width, and then look at the area along with that. So if we create a table to look at this, now we got to remember that we do have a constraint here. We can't just pick any number that we want to. I can for one of the variables, but then whenever I know one variable, the other will change accordingly. For example, let's suppose, for instance, that I choose the length to be 10, and I'm just arbitrarily throwing out a number. Well, if this side is 10, then we know because of this being a rectangular fence, and we're going to assume that we're trying to make it rectangular, nice and neat, then this side is also the length because they're going to match. Opposite sides are congruent in a rectangle. So this side would be 10 also. Now I only have 100 feet of fence to work with. Well, I've used a total of 20 already. So that means this side would have to be 80 in this scenario. So this would have to be 80. And in this situation, my area, of course, area is equal to length times width for rectangles. So 10 times 80 would be 800. That's one scenario. Now let's maybe try a different scenario. What would happen if the length was 20? Well, if the length was 20, then this would have to be 20 as well. So I've got 20 and 20 is 40. Out of 100 means that the width, the part remaining, would be 60. Now notice in these two scenarios that I have not had to use any fencing over here. So I'm not really, whenever I'm figuring out my numbers, I'm not having to say 20 and 20 is 40, there's 60 left, but that has to divide between two. I'm not having to do that because this side is being used by the house. I don't have to use fence over there. That's the cool thing about putting it up next to the house. So in this scenario of 20 times 60, area length times width, 20 times 60, that would be 1200. So you can see this right now is a better scenario than the previous because we have a greater area. So if we're having a pet inside that, whether it be a dog, a cat, whatever, they have a bigger area to walk around in, a bigger walk space. All right, so we understand the scenarios here, and we've tried a couple examples. So here is my question. What are the dimensions of the fence that will create the biggest area? I'm sorry, I forgot to have that there a minute ago. So let me put that, or the largest, put that in. Now we could keep trying scenarios here and come up with numbers, and we may get to a number that appears to be the best. The question though is, how do we know that's the best? And that's where math kicks in. That's where we can kind of start working towards more of a formula model that will reveal to us the best scenario. Okay, so what we got to think about here is what's going on. Think about what formulas are involved. What This is everything going on in this problem. Well, we know obviously that we're focused on area. So I know here in this problem that area is really my main goal here. That's the primary concern. So in this scenario, we'll consider this a primary equation. Okay? Now, that's not the only thing going on here, though, because as we're developing this length and width and this area situation, we also have to operate under this constraint of 100 feet. And this 100 feet is referring to the distance around my pin. So it's almost like perimeter. Notice that perimeter is always like going around an object, whether that be a triangle, a rectangle, square, whatever that might be. So I have what's known as a secondary equation here. And my secondary equation, think about how we're coming up with this. Where do we figure, what are we totaling up to? We know here that we're limited by a perimeter of 100 feet. So I know that whenever I total things up, it has to total to 100. So let's think about what are we totaling? Well, in this situation, we were going 20 plus 20 plus 60, but that was an example. So let's use our variables of length and width. So instead of saying 20 plus 20 plus 60, we could say that my secondary equation would be L plus L plus W. L plus L plus W. Or if I clean that up a little bit, it would be 2L plus W is equal to 100. So we could call this a secondary equation. This is my focus. This is what I'm trying to get towards, but I have to involve or operate under the constraint of this secondary equation. Okay? So with that being said, let's see what we can do with these two equations. So I'm going to move this up. And again, remember, let me rewrite these. So I have my primary equation is area equals length times width, and I have my secondary equation where I have that 2L plus W is equal to 100. Now, I'm trying to maximize area. We want the maximum area. But I don't know anything about length and width. And whenever we're dealing with an equation like that, we cannot solve an equation that has two variables. There's just too many moving parts. So this is where we can use our secondary equation to help us a little bit. So what we're going to do is come over to our secondary equation and let's solve for one of these variables, either L or W. It really doesn't matter which one. So in that case, we can pick the one that seems to be the easiest. And in that case, I'm going to try to isolate the W variable. To do that, it would be actually quite simple. We just need to move 2L, and we can do that by doing the opposite of 2L. So I'm going to come over here and do the opposite. That would then cancel these, and I would have that the width is equal to 100 minus 2L. And if you think about it, that's what we were doing a second ago. When we said that L was 10, then we had two of those 10s. 2 times 10 is 20. And if we take 100 or take 20 off of 100, 100 minus 20, then that left us with 80 for the width. The same thing if we chose an L of 20. 2 times 20 is 40. 100 minus 40 is 60, meaning that the width would be 60. So both this top equation, the original, and this new equation, or this new version, both have the same relationship between the width, the length, and the total perimeter of 100. Now, since we have this other version of this secondary equation, this is how we're going to use this. This is telling us that the width can be calculated or can be represented by 100 minus 2L. And since that's true, I'm going to take this part that is equivalent to the width, and we're going to bring it over and substitute it into our primary equation. If we do that, we get the area is equal to length times, now we're substituting this in, 100 minus 2L. And from there, we now have an equation that is in one variable. Notice that it's not in two variables anymore, but it is now in one variable. And that is something that can now be solved. We can solve it algebraically. We could solve it graphically. In this situation, I'm going to go to Desmos, and let's look at what this looks like on Desmos. Of course, we'll be putting it in using X's so that it'll be something that Desmos can understand for us. So we'll do it as this, X times 100 minus 2X. Okay, so let me grab Desmos and we'll check this out. Okay, so I actually typed it in like the equation we had to begin with. Desmos is smart enough to understand what we're talking about. It doesn't need it as x's, so you can see I did as a equals L times 100 minus 2L. It generates this quadratic graph or this parabola. And that should make sense to you because if you think about it, we're trying to figure out the maximum area. And the only way to have a maximum is for the graph to have a maximum. So in this situation, what we have is a graph where the x-axis is my L and my y-axis is my area. So what we're looking at is if I trace along here, like for example, this point here, this would refer to an L value or a length of 4.1 and an area of 376. Well, I want to know the maximum area. So we're going to go up to the maximum point here, and you can actually see it. If I click on it, it's telling me that that maximum point is occurring at 25, 12, 50. 25, 12, 50. All right, so let's bring this back to our equation. 25, 12, 50. So what I have is, let me just kind of create this illustration here for a second. I have this maximum occurring at 25, 12, 50, meaning that the x value, or in our case it's the L value is 25, and when the L value is 25, the corresponding area is 1250. So that's telling me what my maximum area is going to be, which is what I wanted. I wanted to find the maximum area. And it has told me how to get that by having a length of 25. Well, I need to know the dimensions. So if the length is 25, then to figure out the width, we can go back right here to my secondary equation. So if 25 is plugged in for L, 2 times 25 would be 50. 100 minus 50 is 50. So the width would be 50. So I get my maximum area whenever I have dimensions of 25 by 50. Okay, so if we bring this back and I look at what we have here, this is telling me that my maximum occurs when my length is 25, which means this would have to be 25. 25 and 25 is 50, meaning that this one would be 50. 25 and 50. And you can see what it was telling me if I multiply area's length times width is that it would be 1250, if I remember correctly what that was. Yes. And there we go. We've answered that problem. So that's an example of how we can use algebra and math to solve a real-world application problem. The key is understanding your primary equation, your main goal, which was around creating the biggest area, identifying that formula, and then identifying any secondary equations that are limiting you. And then you can use that secondary equation, like we did here, to create another version of our primary equation in one variable. All right, good luck.